Energy can be split into two main categories: kinetic energy, where things are moving, or potential energy, where the energy is just stored. Some types of kinetic energy would be electricity, electromagnetic, which is just light, sound, and thermal, or heat. And potential energy could be like chemicals, elastic potential energy, gravitational potential energy, and nuclear potential energy. Electricity is just moving charges, so kinetic energy has to do with movement. Electricity is moving electrons. Electromagnetic, or light, is changing electric and magnetic fields. Sound is things that are vibrating, like the reed of a woodwind instrument. Thermal, or heat, is just moving molecules, jiggling back and forth. Potential, or chemical potential energy, is like food. You ingest food, your body metabolizes it, and gives you energy. Elastic would be like springs or rubber bands. You stretch them out. While they're stretched, they have stored energy. Gravitational potential energy would be like taking an object with mass and elevating it above the ground. And nuclear, Einstein's famous equation, energy equals mass times the speed of light squared. So conservation of energy. I think you perhaps have heard this before, so if I just jog your memory a little bit, maybe it would be enough to finish it. Energy can neither be, and I'm hoping you remember that is created nor destroyed. Energy can neither be created nor destroyed. There's a second part to that that says it can only be, and maybe you can finish that, transformed from one form to another. Maybe you're familiar with that already, maybe you're not, but conservation of energy says energy can neither be created nor destroyed. It can only be transformed from one form to another. All right, so we use the word energy all the time, but what is the definition of energy? 3 little lines here is definition. How would you define energy? I'll give you a hint. Energy is defined as the ability to do, can you think about it? Work. We just finished a video on what the definition of work is. Work was defined as force parallel to a distance moved. It is effort and accomplishment. And then we said if the force was not parallel to the distance, you had to find the cosine of the angle to find a component that was parallel to the distance. All right, now we're going to add the last piece to this equation. If energy is defined as the ability to do work, E is our abbreviation for energy. When we do work, we're going to change the energy. We're going to transform it from one form to another. That little piece of the equation right there is called the work-energy theorem. That the amount of work we do equals the change in energy of our system. It takes 1,000 joules of work to transform 1,000 joules of one form of energy into 1,000 joules of another form of energy. You can't create and destroy energy. You can only transform it from one form to another. You do that by doing an equal amount of work. So let's say we had a tall building like this, and here's a brick just sitting on the sidewalk. We grab hold of that brick, and let's say that brick weighs about 20 newtons. Okay, so we're going to put a force on that with 20 newtons, and we're going to carry that up the stairwell all the way up to the top, and then hold it out over the side here. Okay, and let's say that the brick weighs 20 newtons, and we lift it a distance of 50 meters. Well, force times distance, we just did 1,000 joules of work up here. Okay, so the weight of the brick is mass times gravity. So that's what gravity's pulling down, but we as a person had to push up equally to move that brick at a constant velocity up the stairwell. Well, the person did work. The person did 1,000 joules of work, which means they converted 1,000 joules of one form of energy into 1,000 joules of another form of energy. Okay, what was this form of energy? It'd be maybe a little hard to guess, but it's chemical potential energy. It's pancakes. It's what you had for breakfast or lunch or dinner that gave you the energy to be able to do that work. So you're converting energy in your body into another form of energy, which would be called gravitational potential energy. Lifting that mass above the ground gave it gravitational potential energy. So your breakfast allowed you to do work, giving and converting your chemical potential energy into gravitational potential energy. All right, now if we let go of that brick, it's going to fall down and it's not going to be as high, so it's not going to have as much gravitational potential energy. But what is doing work in this case? Well, it's the gravity is doing the work. Okay, so gravity is doing work, converting this form of energy into another form of energy, and that's called kinetic energy. When it's moving, it has kinetic energy. Well, we can quantify these two things here. Just like we said, the work we did on it equaled the change in energy. And this is the equation to calculate gravitational potential energy. We let U represent potential energy. And I know you don't like that. It seems like P or E would be better. We use U. And if you want to blame someone, you could blame William Rankine of over 150 years ago. He's the first person who started using U. Perhaps it's because U and V are similar letters, and V is for electrical potential, like voltage. And anyway, we use U. Nobody likes that. Everybody's upset about it, but the best thing we can do is just get over it, and we're going to use U for potential energy. This is U sub G, so this is the gravitational potential energy. Well, the amount of gravitational potential energy we had was the work we did on it. The work was the mass times gravity, which is force, and times the change in height is the distance. So it's just force times distance. That's a big equation. We want to remember that one. We will use this one a lot. Let's look at the units of that. Mass is measured in kilograms, gravity is in acceleration, so it's meters per second squared, and the change in height would be measured in meters. So if we combine all those units, we get kilogram meters squared per second squared. And if we remember from our video on work, that is measured in joules. This is the common unit, the one word unit, and this is the fundamental unit, or the MKS unit of energy. All right, the other form of energy was this kinetic energy, and that is energy due to its motion, where gravitational potential energy was energy due to its position. And this is how we calculate kinetic energy. We use K for kinetic energy, and we like that one. And that is also another really big equation we're going to use here. So we look at the units. Mass is measured in kilograms. Velocity is meters per second, but that gets squared. So we get kilogram meter squared per second squared. And that is also the units of joules. Okay, so work was measured in joules, and now energy is also measured in joules. Remember these two equations. So we have the work-energy theorem here, that the amount of work we do will equal the change in energy of a system. Well, the energy could increase or the energy could decrease. So that if it's a decrease, that's going to be negative work. And if it's an increase, it's going to be positive work. Well, when the distance and the force are in the same direction, that will increase. That is positive work and will increase the energy of the object. This is work done on the object versus work done by the object. If the force and the distance are in opposite directions, that's negative work that's being done on the object. and that would just decrease the energy of the object. Maybe we should do an example. Okay, so this person is pushing this motorcycle with force, and you're going to move it some distance. It's going to accelerate that motorcycle. It's going to go faster and faster and faster, giving the motorcycle kinetic energy. So the force on the motorcycle was in the same direction as the distance it moved. That increased the energy of the motorcycle. But negative work would decrease the energy of the motorcycle. If that person is slowing it down like this, the force was that way and the distance was that way, and that would be negative work decreasing the energy of the motorcycle. This looks like a really fun roller coaster. And let's say that right at the top here, our initial velocity is 0. I know we kind of crawl over that point there, but we'll keep it simple for now and say the velocity was 0. I would like to calculate how fast we're traveling down here at the bottom. Well, we could have done this with simple kinematics, knowing the acceleration of gravity and x equals 1/2 at squared. Solve for t, and then plug that into the equation for final velocity equals acceleration times time. That's just jogging your memory, I hope. But we have a better way now. This is the actual height of this roller coaster here, 93.6 meters tall. It's really tall. This is called the Steel Dragon. And the idea here is that you can't create or destroy energy, you can only transform it. So all of this potential energy up here will be transformed into an equal amount of kinetic energy down here. So the potential energy, the gravitational potential at the top equals the kinetic energy at the bottom. That's the physics. If you can do that, you have found your equal sign and the physics is done. The rest is algebra. That gravitational potential energy is mass times gravity times the change in height, and the kinetic energy is 1/2 mass times velocity squared. Notice that we have mass on both sides. It cancels. That means it doesn't matter if the roller coaster is filled with large people or it is empty, the velocity will be the same at the bottom here. So I have 1/2 here. I'm going to multiply both sides by 2 and then take the square root to get velocity by itself. And then I can, once I have it solved for velocity, then I can plug my numbers in. This was gravity, this was height, and I find that it's going to be going about 42.8 meters per second right there at the bottom. As it's lost all that potential energy, it will have this velocity, which would give it an equal amount of kinetic energy. That's about 95 miles per hour if you did the unit analysis on that, converted meters into miles and seconds into hours. All right, well, so that's how fast they're going down here, 42.8 meters per second. Let's see how fast they're going to be going when they reach this point here. This is going to be a little more complicated because in this problem here, they're going uphill and they're losing kinetic energy. So the change in the gravitational potential energy is a loss of kinetic energy. Well, if I multiply both sides by negative, I can just put the negative on this side. It may not make complete sense right now, but as I proceed through this problem, I'm going to have to take the square root at some point. And if I didn't do that, I would get a negative inside the square root, and that's never good. So the change in potential energy, the negative of mgh delta y, is equal to the change in the kinetic energy. So right here, it had some kinetic energy. That's its initial kinetic energy. And then we have a final kinetic energy. So we have the final kinetic energy minus the initial kinetic energy. The difference of that is the change in kinetic energy. And see, I have mass in every term here. It will cancel. So then I can take, and I have a half here and a half here. I'm going to multiply everything through by 2. And I'm trying to find out how fast it's finally going to be going. I will add this term to both sides. And then that's what final velocity is squared, so I have to take the square root. And this is where I was saying that if you weren't careful with your negative, this number here would have been positive and this number would have been negative. You would have gotten a negative inside the square root. And you would have figured out that you would have had to have done something different. So that's where we did this piece right there. Plug the numbers in, and I find we get 24.2 meters per second. right there. It's going to be going slower. So 24.2 meters per second is about 54 miles per hour, which is still pretty fast through that turn there. All right, let's see if we could have gotten that number a different way. Okay, so instead of going 63.6 meters up here, let's do the 30 meters down from the top, because remember the whole thing was 93.6 meters. Well, this just turns out back to that simple problem that potential energy at the top equals the kinetic energy at the bottom. Mass cancels. We multiply both sides by 2 to get rid of the 1/2. Take the square root, plug the numbers in, and we get the same thing we did that way. Okay, so either we could have say what the change in kinetic energy was here by looking at the change in potential energy, or what the change in potential energy was here and how much kinetic energy it would have there. Now let's do one other little piece to there. Let's say that this roller coaster here has friction on it, that as the wheels roll, they don't roll perfectly free, or as that roller coaster is moving through the air, there's air resistance on it. But let's say that there's an average frictional force of 942 newtons on that thing. It's not going to be going that fast down there anymore. So how do we deal with that? How do we incorporate this number into an equation that will give us velocity? Well, the potential energy that it had up top here was that amount of energy was converted into two things. Kinetic energy, the roller coaster was moving, but then a little bit of work was done as well. The work was force times distance. Okay, so now that was the physics. If we can do that, realize that the potential energy at the top was converted into two things, kinetic energy and work. That work is going to take some of the potential energy and turn it into heat, like friction in the wheels and stuff. And it will actually warm up the air that it passes through because it's making that air move faster now. So that's the physics. Now we plug the numbers in. And notice this time, though, that mass does not cancel out. There's a mass here and here, but to cancel mass out, we would need a mass in this term as well. So let me give you the mass of this. And that makes sense because if that roller coaster was empty and it still had this much force on it, well, that would affect its motion a lot more than if it was a very, very massive roller coaster. Okay. So I gave you the force of friction, but the distance here, this force of friction is acting through this distance here, which we'll say is 178 meters. Okay, it's not this distance here, it's the actual distance that it moved. And this is an average force, okay, because as it's going slow, there's not a lot of air resistance, and as it goes fast, there's more air resistance. Okay, but so anyway, that's potential energy equals kinetic energy plus work. So then I'm taking the work and I'm moving it to this side because I'm trying to figure out how fast it's going. I'm going to multiply everything through by 2. So this by 2, that by 2, and that by 2. And then I'm going to divide by the mass to get the velocity squared by itself. This mass does not cancel. We would need a mass here and a mass there to cancel. Or if the mass were outside the parentheses, it would also cancel. Okay, trying to get velocity by itself, I square root. Once I have velocity solved for itself, then I can plug the numbers in, and I get 41.5 meters per second. Without friction, it would have been going 42.8 meters per second, but with a little bit of friction, it's going a little bit slower. Okay, but this friction we just incorporate into this equation because the friction is doing work on that. It's applying a force over that distance. It's going to be going about 92.9 miles per hour. This is an interesting problem, that if there's an accident and there's skid marks left on the road, you can calculate how fast that car was traveling when it hit the brakes. And I'll tell you, as a physics teacher, I've been hired several different times by lawyers as an expert witness, where the police do a report and they measure the skid marks, but they have to hire a physics teacher to analyze that data, and they pay me pretty good money to do that. But it turns out to be a fairly simple problem. How fast was the car traveling when it hit the brakes? All we need to know is the length of the skid marks and the coefficient of kinetic friction between the tires and the road. Okay? Because this is the work energy theorem, that however much kinetic energy the car had before it hit the brakes, to get rid of that much kinetic energy, we've got to do an equal amount of work. So the force of friction over that distance is what's doing the work. All right, now we have to remember what force of friction was. It was the coefficient of friction times the normal force. How hard the tires are pressed against the road. I should say that it turns out to be this because the road was level. If the road was not level, we would have to find components and draw a free body diagram. Okay, now I can't quite solve it yet because I don't know the mass of the car, but how hard the tires are pressed against the road is just what the car weighs. So the normal force is the weight of the car, mass times gravity. And that's where the mass cancels out. And if I multiply both sides by 2 and then take the square root, I can plug the numbers in and find that it was going about 18 meters per second. You probably want to know how fast in miles per hour that is, or in kilometers per hour. So I'll let you pause and convert that using unit analysis. All right, so let's do another example with what's called stopping distance. If a car here is going 30 miles per hour, and right when they hit that yellow line, they hit the brakes, I think 20 feet is a reasonable stopping distance. 30 miles per hour is kind of what you would do in a residential area, maybe a little fast. But aggressively stopping, maybe you could stop in 20 feet. But let's just assume for a moment that that is a reasonable answer. What stopping distance would we do if we were going 60 miles per hour? Well, 40 feet, right? Twice the velocity is twice the distance. We got to be careful. The change in energy is equal to how much work needs to be done. This kinetic energy needs to disappear. It needs to go to 0. So we have to do an equal amount of work here. But look at the velocity. It gets squared. If we had twice the velocity, we would actually square it and get 4 times as much kinetic energy. And if we apply the brakes with the same amount of force, it would take 4 times the distance to come to a stop. So if 20 feet was reasonable here, 4 times that would be the reasonable number here. If we were going 90 miles per hour, 3 times as fast, what distance would it take to stop? Well, 3 times the velocity. If you square it, you get 9 times as much kinetic energy, so 9 times the stopping distance. It's going to take 180 feet for that to come to a stop. All right, let's do this problem with a pendulum swinging back and forth. You pull the ball back like this, and we want to figure out how fast it's traveling right there. It raised up 0.6 meters, and as the ball swings back and forth, it's going up and down, it's going faster and slower, but the total amount of energy is remaining constant. So how fast is it traveling right there? Just potential energy up here, converted into kinetic energy down there. It's the same problem we've been doing, and about 3.4 meters per second. All right, let's do this one. Let's say that we pull this ball back to our chin up here, and we want to figure out how high it will come when it comes back. Okay, so how high will the ball rise upon return if the ball pushes against air with an average force of 0.3 newtons, tiny amount of air resistance as it moves through the air, but as it goes a distance of 5 meters. So from your chin, it's going to go 2.5 meters that way and 2.5 meters back, a total of 5 meters. Okay, the change in potential energy, gravitational potential, is going to equal work. So we're going to solve for how the change in height this time. Okay, how high will it come back? So the force of friction was 0.3 newtons, the distance was 5 meters, mass is 8, gravity is that. The change in height is going to be 1.9 centimeters less. So if we pull that back to our chin here, a height of 0.5 meters, when it goes there and comes back, it's going to come back this much less. So 0.5 minus that is only going to come up 0.481 meters, not going to hit your chin. So here I have my iPhone braced against my lecture table, and I'm going to pull the bowling ball right up to the phone like this, and it goes there and back, and I do not have to worry about it smashing my iPhone. To see it here, there, and back doesn't ever come quite as high. All right, I want to do springs here real quick, but let's remind ourselves about just force and distance. That if the force was constant through that same distance, we can find the area under that curve and it would give us the work. A spring, very little force at the beginning, but more and more and more force as we push it further and further and further. So the area under that is going to give us the work we did. Okay, it's the average force times the distance. The force of a spring is kx. So if this is the full displacement up here, if I multiply it by the spring constant, I will get how much force there was up here. So that's this here. Half of that would be the average, and then I have to multiply it by the base here. So the force times the distance divided by 2 is the work that we did. So this is another equation we're going to check off here, that the potential energy of a spring is 1/2 kx squared. 1/2 kx squared. Because the potential energy of the spring when it's compressed equals how much work we did on it to compress it. So if I have a ball here and I push that ball, I'm doing work on it, and I'm compressing it 0.5 meters. This spring now has all sorts of spring potential. It's storing that energy right now. So the potential energy of the spring will be converted into kinetic energy of the ball. So the potential energy when it's right here will equal the kinetic energy when it's fully sprung back. They always preface and say this is a light spring, because as this spring stretches out here and pushes against the ball is going to gain kinetic energy. It's a moving mass, but the spring, if it's not light and has a lot of mass, then it has some kinetic energy as well, because it's going to be moving real fast. So we always say it's a light spring so that we don't have to consider the kinetic energy of the spring itself. Okay, but I'm just going to take that equation and solve for the velocity, and that ball is going to be going 2.5 meters per second when it gets back to this spot right here. What's going to be different in this case? Instead of shooting the ball horizontally, we're going to be shooting the ball upwards. So we're going to take that ball and compress it down. It's probably not going to be going quite as fast when it gets back to this spot as it was in the previous example. So we have to adapt our equation. What goes there? Well, the ball is going to be moving up, and it's going to be gaining some gravitational potential energy. Okay, so the ball is going to get some kinetic energy. It's going to be moving here, but it's also moving up, so it's gaining some gravitational potential energy. Now let's put the ball and spring inside a tube here like this and push it down. And there's a little friction. The ball is going to be rubbing against the sides of this tube, and we want to figure out what we have to change here. Well, if there's friction, there's going to be work done on the ball. So the potential energy gave some kinetic energy to the ball, gave some potential energy, gravitational potential energy to the ball, and then also did some work on it. Okay, so that's the equation we would have to solve. Let's do one more problem here real quick, and it involves jumping with a bungee cord. So this person here is going to fall a distance of 100 meters, over 300 feet. And we want to make it so we want to choose the right spring constant so that when we land in we can just dunk our head in the water here and be perfectly fine. So here we are in this cage up high here, and we have this bungee cord, and we're going to jump out like this. We'll say the bungee cord is 75 meters long. We're going to jump a total distance of 100 meters. So if the bungee cord is 75 meters, we're going to fall 75 meters before that bungee cord ever reaches its unstretched length. But when we fall 75 meters, then the bungee cord is going to stretch 25 meters, because that's where the water is, and all of the energy of stretching that bungee cord is going to be done in that 25-meter distance. So here's the idea. Right here, the person has some gravitational potential energy based on their mass, their gravity, and this height. And when they get to the level of the water, all that gravitational potential energy needs to be transformed into spring. We're treating the bungee cord as if it's a spring. Okay, so that's the physics right there. And if you can do that, you can do this. So we do need to know the mass, but we're going to solve for the spring constant. Okay, how many bungee segments do we need? And we solve for that, and we get a spring constant of 204 newtons per meter spring constant. That's a little bit with energy and its transformations.